Thank you for your introduction, Wilger. Indeed, it's about creating a constraint programming application. I have 2 points on my agenda. First, I will give you a brief introduction to constraint programming, but most of it will be about the planning of the staffing of a nursery home. And well, let's get started with constraint programming. So what is constraint programming? It's about modeling, and it's easiest explained via an example. Consider a very simple example, the kind of hello world example for constraint programming. We have 3 persons to do the shifts of one day, and the first shift cannot be done by persons 1 and 2. And so how are we going to model this hello world like application? So there are 3 shifts, and there are 3 variables, each having the values 1 to 3 being a shift. The first person cannot do shift 1, as can the second person, and of course they all have to staff different shifts. So these are the constraints and the variables of that very simple problem. In order to solve this problem, a very naive method would be to try each possible combination of the variables xi, and then see whether all the constraints are satisfied. This is naive because we have 3 variables, 3 possibilities, and we have already 81 possible solutions to consider if we should use this method. So how is this done in actual constraint programming? Well, in actual constraint programming, we have an alternative between trying values and deduction. First, we start with deduction, and we can already see that the third variable should be 1 because it's the only alternative given the constraints that x1 and x2 are not equal to 1. Then we can do no further deduction on the variables. Then we will try, and we will say, well, hey, let's try the first variable to be 2. And another postponed possibility would be to try x1 equal to 3. At the first branch, we are going to deduce again. What can we conclude? Well, if x1 is 2, we can conclude that x2 is 3, and we have a solution found for all 3 variables. And we did not even investigate the second branch. So, using the constraint programming solution method, instead of trying 81 times whether all constraints are satisfied, we only have to try once. So what algebra can we use to write models in constraint programming? First of all, it's about discrete variables. So we have integer variables with a typical integer range written in AIMMS as follows, or we have element variables whereby we say, well, hey, the range is a discrete set, say a set of employees. And then it's the constraints in constraint programming are the most powerful part. We combine the discrete variables to values and variables as follows. We can create expressions using any of these operators, including the comparison operators, the min, max, the and, the or, things we are not allowed to do in mixed integer programming, not as arbitrarily as in constraint programming. Another nice feature of constraint programming is that we can write a constraint as an element variable should be in some set, or a tuple of variables should be in some relation. Especially this one is often called a table constraint in the literature, and is a very powerful concept. Finally, something we cannot have in mixed integer programming either is that we can index and use a variable to do the indexing of a sequence of constant values or even in a sequence of variables. And of course, that is the if-then or the if-then-else and if type of constraint. Furthermore, constraint programming has so-called global constraints. These are combinations seen in literature very often of a type of constraint, and a lot of effort has gone into deduction techniques for reducing the solution space. Most prominent, most famous one is probably the all different, but also channel is a very useful one, and well, the others as well, I should say. There are also powerful scheduling constraints, but this will be detailed in a later webinar, not this webinar. Okay, so let's look at the channel constraint for a second. It's it allows you to invert two variables like this. So the inverse of x is y and the inverse of y is x. So you can write, if you have this relation, you can write constraints both on x and y. And as you can see, it's not simply the first is mapped on the first. No, it can be this way. And once you have that, it really helps in the deduction at each node. So now I'm going to the actual application, which is the more interesting part, I think. Let's consider rostering 4 nurses or employees on a weekly repeating roster of 7 days, and each day has 3 shifts of 8 hours, and of course a free shift. And we have some extra requirements. We want to distribute the 3 days equally, or almost equally, because 7 days cannot be divided exactly by 4. We want to ensure that there are at least 18 hours between work shifts. For each working shift, we want to minimize the number of nurses that staff that shift. I'll come back to this requirement, don't worry. And even more strict, I want to minimize the number of transitions from one day to the next for each nurse, for each day. And finally, I want to pay attention to the application performance. So let's start with the first question. We can look at the layout of the solution, and we can say, well, a roster is defined by the shifts and which nurse works on which shift. So we have an employee assigned to a shift. Alternatively, we can say, well, hey, instead I want to take the view of the nurses and see whether a nurse is free working on a particular shift each day for all of the nurses. So my first question to you is, should we model by assigning nurses to shifts? Should we model by assigning shift to nurses? Should we model and use both these variables, these indexed variables? Or should we have a different representation altogether? Remember, this is a very essential choice in any constraint programming application, as the choice of variables defines what you can express on them. So please take a minute to make up your mind.
Okay, Chris, I started the poll, so everyone can now fill in the answer. Not everyone has voted yet. Okay. Yeah, okay.
Let's continue.
Yeah, let's continue. Close the poll. And shall I share?
Okay, Wilger, how many people have chosen C? Which percentage?
56%.
Okay,
And
great.
22%. Oh yeah, 20.
Yeah, please continue.
22% A and 22% had B.
Okay, well, the choice would be C. It's perhaps non-intuitive as it doubles the number of variables, and as I said at the start, each well, there's an exponential number of possibilities created with the number of variables. So it increases the solution space significantly, but not really. Look at the channel constraint. Suppose the first variable is fixed for a particular value. Let's say this one is fixed for, well, this one is fixed here, but given this choice, the deduction of constraint programming immediately fixes another variable due to the channel, and so for each choice made on this first variable, we can link the second variable as well. So it does not really increase the solution space, but it does give you two views on which we can formulate our constraints. And we are going to use both views in the next setup. Okay, so let's view a particular solution that is possible. As you can see, it's not an even distribution, as nurse A has on Monday, Wednesday, and Thursday free, so she has more free than the other nurses. Well, that's not fair. So we want to add a constraint that says, well, the constraint each nurse should have 1 or 2 days free. And how do we ensure a proper distribution of these 3 free days? So this will be my next question to you: how to distribute the free days. Well, one approach is simply to say, well, nurse A has Monday, Tuesday free, nurse B Wednesday, Thursday, and so on, or use a different pattern with 3 days apart, but essentially the same mechanism, just fixing the variables for. We can also do it by adding a constraint. Say we count the number of days a particular nurse is free, and this should be less than or equal to 2. We can use the global constraints in a similar way, a so-called counting constraint, whereby we say, well, hey, this nurse is free. We put the result in another variable, and we limit the range of that variable from 1 to 2. And, well, hey, we can take a step back and say, well, I don't really consider this to be a relevant restriction. Perhaps this is what we want. Some people want 3 days free, some nurses want only 1 day free, so I'm not going to add this restriction. Then these are the questions. Again, I suggest you take half a minute to consider your options. Which answer is the correct question? Wilger, it's yours.
Okay, I will launch the poll now. The votes are coming in.
Thank you.
So let's wait a few seconds and now we'll close the poll again. Okay, I will close it down now and I will show you the results.
Okay, how many people had answer C or D together?
90%.
Okay, correct. Because well, A, B, that's not constraint programming. It's actually potentially excluding interesting solutions. So that's not a good approach. C and D are equally correct approaches, so both are correct. And E, well, I think that for this particular application, it's not solving a problem, but creating one if we wouldn't take care of it. But that's my opinion, of course. And again, I've written an example application, but I'm not going to show that. But I used the answer D myself. Okay, another question. When we look at the solution again, we can see that it's rather chaotic. If we take the shift view, we say that, hey, there are 4 nurses on the staffing the first shift, there are 3 staffing the second shift, and there are 3 staffing the third shift. That may come across as a bit chaotic to the people living in that nursing home. So actually we would like to limit the number of nurses per working shift. And well, let's try to bring it down to 2 different nurses per shift. So how can we do that? This is a question that takes a little bit of time, so let's look at the possible answers one at a time. So the first possible answer is that, well, hey, we say there are 2 possible nurses for the day shift, so let's introduce a variable for the first and the second nurse, and each day, the day nurse is either the first or the second chosen nurse. Similar for the evening and night shifts. Well, this looks a bit verbose, so perhaps we could do it more algebraically. Say, well, for each shift S, it's the first or the second shift nurse. Essentially, this is the same, of course, and we can do it even more algebraically using the exists operator instead of the or. Or we can say, hey, the above is not correct, and actually this restriction cannot be modeled using constraint programming. Please take a minute to answer this question. Wilger, the floor is yours.
Yes, okay, thank you, Chris. I'm not sure how. Let's look at this first. I will launch the poll afterwards because the poll is a bit more limited in the length of the answers.
Indeed.
Okay, I will launch the poll now. Okay, almost people are still voting, so we'll wait a few seconds. Okay, still people voting. Okay, I will close it down and show you the results.
Okay, how many people did vote for answer D?
None.
Ah, good, because that's the only wrong answer. Answers A, B, and C are all equivalent and correct, just a difference in verbosity. C would be my personal choice, as it is the most easy one to extend to 3 nurses in case the 2 didn't work. Well, as far as constraint programming goes, I hope you didn't choose answer D. Another fourth question is, well, imagine you're a nurse yourself and you would do the night shift on Monday and the day shift on a Tuesday. That would mean you would be working 16 hours in a row, helping people, 16 hours on your feet and intense work. But you can imagine you would like to avoid such a situation. So how should we model this in our application? Well, the first possible answer is to say, hey, I only change my shift if there's a free day in between. And so here I have that each day, the next day, so for if I have a working shift on day D, then on the next day I'm doing the same shift or I'm free. That's essentially what this if-then constraint says. Or we could look a bit closer and we could say, hey, there are 2 shifts that are actually the problem here. That is the evening shift. I shouldn't be doing the day shift then, or in other words, the next day I should be doing the free evening or night shift if I'm doing the evening shift on day D. Or if I'm doing the night shift is also a problem. So if I'm staffed for the night shift, the next day I should be doing only the free shift or the night shift, not the day or evening shifts. A third option is to say, hey, there are a limited number of combinations for what I'm doing on day D and on what I'm doing on the next day. So I enumerate those into a relation, say R, and I add as a constraint this table constraint. Please take again a minute to decide which is the correct answer and vote. Wilger, dus the floor is yours.
Yeah, thank you, Chris. I will wait a few seconds before I start the poll because it's a lot of information on one slide.
Indeed.
Okay, I will launch the poll now. Okay, votes are coming in. Okay, I will close the poll now. Everyone has voted. And I'll share the results.
So how many people did vote B or C?
Percentage 31% B and 62% C and 8% A.
Okay. Well, both B and C are correct. Answer A will actually limit the number of solutions and possible interesting solutions, and yeah, well, it's a more restrictive constraint. As I said, B and C are precisely implementing the restriction, but there is difference in formulation. C is a so-called table constraint. A table constraint is not always without comment. A table constraint will not tell you much about what is being implemented. However, they can be much more efficient, especially when the table is very sparse. However, I tried this on this implementation, and if-then constraints of B and the table constraints of C are more or less equivalent in performance. But that is because the table constraint version is not sparse here. So if you can get some restrictions combined into a table constraint, please try to use that in your constraint programming application. On to the next question. There are 10 staffing changes marked in the solution below. Can we actually minimize the number of staffing changes? For example, if we look at the evening shift, we see that there are 4 staffing changes, Thursday to Friday, Friday to Saturday, Saturday to Sunday, and Sunday again back to Monday. If we would have swapped Friday and Saturday, there would only be 2 staffing changes for the evening. So can we get a solution with 2 nurses per shift, per working shift, and less staffing changes? And how should we model that? Well, we do. Here we are minimizing, so we are formulating an objective, and I formulated the following alternative objective definitions. First, we could look at the shift variable. Say, hey, what is the shift from an employee to the next, and see if that changes. We could also look at the shift variable and see whether a shift from non-free days is not equal to the next and count that. Or we could measure the deviation between shifts, like a linear programming model does. So we introduce 2 non-negative variables and see how much difference is created. And we minimize the sum of these deviations. The same one, except that we include exclude the free shift. Please take a minute to see which objective has your preference. Floor is yours, Wilger. You can start the poll whenever you like.
Okay, thank you. Let's wait a few seconds so everyone can read the answers. Possible answers. Okay, I will launch the poll now. The votes are coming in. Almost everyone has voted. I will wait a few seconds. Okay, I will close the poll now and show the results.
Okay, how many people did answer? Did choose B as the best answer?
45% and 18% C and 36% D, and none chose A.
Well, B is indeed the best answer. A is indeed about the wrong variable, so that's a bit of a, but good that no one chose that. C and D measure distance, but well, the difference between the C and D would be 1 if we measure the distance, but it should be equal to the difference between A and D. So we should be counting differences, not measuring it. Measuring distance. So that's B is the correct answer here. Okay, then what people like most about constraint programming is how to formulate it in such a way that we reduce the solution time. And that often takes some thought. A first technique is to reduce the solution space. So how can we reduce the number of solutions that need to be considered, that are potentially to be considered? As I told you, we have a shift variable, which has 21 individual variables. Each individual variable has 4 values, so we have a solution space in the order of 10 to the 16. And well, that is really a lot of number of solutions, and don't want to go through all of them. So how can we reduce this number? Now, the first method is, well, again, to formalize heuristic and leave some freedom after the first solution is found for the optimizer to find. A second technique is, hey, we see that the employees, that it doesn't matter which shift is started on the first day, because none of the employees has been restricted, so let's start the first day. Or we could say, well, hey, there's symmetry in days, let's reorder the days and reduce potential solutions thereby, adding just another constraint. Or, hey, why not use all of the above techniques? Please take a minute to select your preferred choice. Wilger, please start the poll at your convenience.
Okay. I think I can launch the poll now.
Oh.
Okay, the votes are coming in. Okay, almost everyone has voted now. We'll wait a few seconds for the last few votes. Okay, and we'll close down the poll and show you the results.
Okay, how many people have voted for B?
It's 50%, and
okay.
C 10%, and D all of the above 40%.
Well, B is the correct answer. A doesn't fit the constraint programming paradigm. It is actually reducing the number of possibilities to be searched, and well, C is not correct. There is no symmetry in days because we have restrictions going from one day to the next, so we can't arbitrarily reorder the days. Well, as A and C are not correct, D is neither, and B is the remaining correct answer. Then I'm going to another technique. It's the so-called redundant constraints. Redundant constraints are constraints the optimizer can't deduce itself from the given constraints, but a human can, and these redundant constraints help the deduction steps taken by the constraint programming, reducing the possible solutions of each variable after each branch taken. So my seventh and last question is, which other constraints can you derive from the given formulation? I have a few choices, perhaps there are more, but these are mine. If you remember the counting constraint at the second question, the amount of free days, then you can say, hey, if we look at the employees, the sum of the employees, the sum must be 7, obviously, because there are 7 free days. The second one, the objective is greater than or equal to 6. It takes a bit of time to see why this is so. We have for each working shift there are 2 nurses, so there are at least 2 changes from one nurse to the next and back for each working shift. As there are 3 working shifts, this means that the objective is at least 6. So we cannot have a solution whereby there are 5 or less different staffing shifts. Well, obviously we haven't. We can use all different aspects here, both on the shift and the staffing variable. And hey, all of the above are actually redundant constraints we could add to the model formulation, hoping that they would reduce the solving time. Wilger, again for the last time, this is the last question. The floor is yours.
Okay, thank you, Chris. Well, the short answer, so I think I can launch the poll now. So I will do that. Okay. Please vote. They're already coming in. Okay, still waiting for the last few votes, after which I will close down the poll. Okay, we'll close the poll. Now I'll show you the results. Most people chose for D, all of the above. Then second favorite was the C, 20%, and 10% chose for A, and none for B.
Okay. Well, actually, B turned out to be the most helpful one, because the solver, in my testing of this application, the solver tried to prove there is a better answer than B, and when I better answer than 6, and when I added this constraint, it was on finding a solution almost immediately. But indeed, D is the correct answer. So that's it for now about creating the constraint programming application. I would like to announce the next webinar. Now, it will be given by Peter Nieuwensteeg, my colleague, on May 20th, and it's about the Mathematical Program Inspector, the tool to help you inspect your mathematical programs created.